So the last time we left off, we were looking at the different probes, the configurations of those probes. I know what I forgot, I remember now. Different probe configurations, and I talked about, probes or coils can have one or more coils in them. So some examples of bobbin probes with multiple coils that create fields in other alternate directions versus kind of these pencil probes down here and the spring-loaded probes that are they kind of have a single sensor on them. They may have two coils. They may have a driver, what's called a driver and a pickup. We'll look at in a second. But they do that. So looking at the internal construction of them, so the probes, how they're built with the coils that they have, are going to work with the tester in different ways. And so our tester, it's important when we set up our tester, which is the test, now I'm talking about the test unit, the cable, the probes that you're hooking up to it, that it's important that you match everything up so that it works correctly. And so you typically there's kind of 4 different types of probes. 3 are your kind of standards. So there's what are called absolute probes, differential probes, and then there are reflection type, and there can be just straight reflection/differential, which kind of falls under the 4th category, which is hybrid probes. So on most of your testers, you have the ability to select between one of these 3 types of probes, absolute, differential, reflection. The hybrid probes can often have kind of attributes of one or more of these. And so when you're working with a hybrid probe, it will tell you how the tester needs to run that probe. And it might be a hybrid probe, but you set your tester as an absolute. Or it might be a hybrid probe, but it's more in common with a differential, so the tester would run it as a differential probe. Or it's a hybrid probe with reflection. So that has to be done, and in many cases, your newest equipment, your most expensive equipment, can do this automatically to some extent. But most equipment you're going to run into, even today, even the equipment that's capable enough for what we're doing, you're probably going to have to set it manually, including everything we use in our lab. You're going to have to manually select it. So you have to know, what type of probe you're using, and if it's a hybrid probe as well, what to set your tester to. But each one of these can have the number of, 1 or more coils. They can be wired in different ways, and some may be powered, some may be unpowered, depending on the probe setup and what it's trying to do. So absolute probes are kind of the simplest type of probe out there. And these are a single coil that is both the generating coil and the pickup coil. So it's going to create those magnetic fields and eddy currents, and it's going to ultimately sense that change in inductive reactance that's caused by those eddy currents and the magnetic fields that they put off. And so these are probably one of the most common ones used. They're one of the least expensive because of their simple construction. And they're often used for things like surface cracks. They work really well for small surface cracks. They tend to be fairly small coils. They can be used for other things you can see here, like conductivity, material sorting, and alloy, because if you're in a case where all you need to know is what am I putting in front of the probe, it doesn't need to have any kind of special penetrating ability or anything like that. It's you put a material in front of it, and if it's material A, the inductive reactance is going to change one way. If it's material B, the inductive reactance will change another way. And so you can use it for those kind of sorting or alloy content situations. But they do sometimes, you just got to be careful, they are wired sometimes with what's called an air-loaded reference probe, or an air-loaded reference coil, which even air temperature affects the density of the air. The density of the air can affect how the inductive reactance of the coil. It's very small, right? It's a very minimal difference. But if you are if you need that extreme level of precision, you might need to compensate for those changes in air density. And so, which also can be moisture content, temperature, pressure, all that. And so you'll have a coil that's air loaded. It doesn't have any kind of a core in the center of it where it'll compensate for those changes, that changing environmental conditions. When we're using one of these, the most common kind of indication that we see looks something like this. So here's our instrument. They say CRT. Ours are now all flat screen. You can tell it's a little bit older illustration. But you have your impedance plane indication here. And so what they're showing is you start with your probe, and they're showing A is actually up in the air. Okay, you have, and as you set it down onto the part, as you bring it closer to the part, that inductive reactance is going to change until you get to point B. And point B is what we call our neutral point, or our origin point. And so that point B is where we'll start with our probe on the part. Then we're going to start moving our probe across the surface. And so here is, they are showing what's called a crack standard. It's a block of metal, and it's going to be the same type of metal you're going to be working with. So it'd be like an aluminum block. And you'll use these. You're going to do this exact same test in lab. But you will then move that probe across different simulated cracks. And these are manufactured for you. They use something called, it's called an EDM, electric discharge machine, to make these very, very fine cracks. So you'll see them on our blocks that we have. They can be very, very tiny. And right here, these cracks are the same width, maybe 20 thousandths of an inch or even 10 thousandths of an inch. But you can see as the depth varies, C, D, and E, you're going to get different indications. So as the probe goes across C, it's going to move, the point on our impedance plane diagram is going to move from B up to C and back down to B again as that probe passes that crack C. Okay? So as you start to get close to the crack, as you start to bring the right side of the probe over that crack, it's going to move up a little bit. And as the probe continues to move more, it's going to move up more. So what it's showing right now, where the probe is centered over C, is where the indication would be at point C on the diagram. And then if you were to clear your screen at that point and continue moving it, it would then draw another line back to B. Most of the time it draws that line and comes right back. So you can't see that there's actually two lines there. But each one of those, the line going from B to C, and then from B to D, and then from B to E, it's a line over time that's been drawn out to that point and then back again. And that's as it's affected more and more and more by the coil, or by the crack. The coil is affected more and more by the crack, and then less and less and less by the crack as we pass over it. And so you can see D makes a larger indication, and E makes the largest indication. So you can not only find that there is a flaw, but you have some ability to judge the size of that flaw. If you know what the depths of these various standard cracks are, our known standard block to compare against, we can give us some idea of what we're dealing with when we inspect our part. So Absolute gives us these very simple single line drawings typically, and it's used for those surface cracks. These are your like pencil probes, your spring-loaded probes, very small coils. The next type of probe we have uses two active coils. So this is a differential probe. So when I say active coils, it means both coils are being driven. They're having that current run into them to create a magnetic field. And they are both sensing those resulting eddy currents in their magnetic fields in the parts. And the tester is essentially looking at the difference in inductive reactance between the two coils. That's where the term differential comes. It's taking one, comparing it to the other. It's taking one, subtracting it from the other. And when there's a difference in one coil or the other, it's going to pick that up. And so the signal or the flaw is detected by both or either coil, and it's looking at the difference in those two coils. So They're extremely sensitive to defects, but what can throw them off is if you have a gradual change in material thickness or a gradual change, like a large area, you're not going to get much differential between the two coils, right? They're going to see a sudden crack. They're not going to see slight changes as well. And so they're, again, used more for crack indication and that kind of thing. Probably less for thickness measurements, less for backside corrosion, which tend to be more tapered, more sloped, and that kind of thing. They're very forgiving. The probe wobble or inconsistent coupling is what it's called, where it doesn't stay flat on the surface. That kind of gets filtered out by those two coils. It's a subtle enough difference that both coils are kind of picking it up, and so both coils are kind of ignoring it. It's really looking at that difference between the two coils. And so if the other thing that happens is if you have a very large flaw, again, like a corrosion or something that's wider than the spacing of the coils, you might get a miss because, again, we're looking at the difference between the coils. If the flaw is larger than the coils, than the physical location of the coils, you're not going to get much difference between them, right? They're going to be picking up the same thickness or the same flaw. So you won't get much of an indication. So these tend to look something like this. Because they're differential, what that means, you can see how these are wired. They are wired in opposite to one another. They're wound in opposite directions inside of our probe, the two coils. And so by being wound in the opposite direction is as we start to go across a flaw, you're going to get that inductive reactance change in one side and then the other side. And so they often create this kind of bow tie shape that you can see here in E, in E. Because as we go across in A, it's showing right here we're over a non-flawed area. So our point is going to be right at the origin. It's going to stay right here at the bottom. And then as we start to go across a flaw, it's going to move one direction. And then as you get back to the center, you can see in C, where the crack in this case is directly, kind of equal underneath the two coils, it'll actually return back to the origin point. And then as the second coil in D starts to go across it, it's going to pull that inductive reactance, that indication, the opposite direction. And then again, in E, we're past it, and we've gone back to the origin point. So this is a common way to see it. I've also got this display over here on the left. There are cases where it can look similar to that absolute probe, but it gets this little hook on the end. Okay? And because you get a stronger reaction when you're initially going over the crack, when you start to go over it here, like B, right? It's close enough that this left coil is probably also starting to react, right? There's a change in inductive reactance both times. So when the crack is big enough that it can affect both at the same time, you'll get more of this impedance plane diagram on the left where it kind of looks like an absolute probe, but it gets that hooked end on it. And depending on how far you're zoomed in or zoomed out, you may or may not see that hooked end show up. Okay? But if you have a very small crack, especially one where the probe itself, the coils are larger, you'll often get this bow tie shape, where there's a big enough difference in size between the probe face and the flaw. And then our third type is a reflection probe, third general type. And so a reflection probe is now we are using two coils again, but instead of both coils being powered, only one is. One becomes what's called the driver, and the other one becomes the pickup. So one is generating those eddy currents, generating those magnetic fields. The other one is purely being affected by them, the passive pickup coil. And so this is where, when we're setting up our equipment, how is our equipment looking at the inputs and the outputs from those coils? That's why we have to match the equipment to the coils to do that. So we detect the impedance change in the second piece, and now what we can do is start to optimize the coil sizes. So typically, if we want to send more power, if we want to generate stronger fields, we have to create a bigger coil. Right? We can only run so much power through a very small coil. We'll burn it up if it's too high. Right? Or we will, in the case of a a differential or an absolute coil, if we're running too much power into it, we may not see the flaw coming back out of it. It may overwhelm any effect that you would have from the eddy currents in the test piece. So there's limits to how much you can drive the coils in a absolute or differential probe. But here we can have a larger coil, heavier duty coil that we can run more current through to create a stronger field that affects the part, which creates stronger eddy currents in the part, which creates stronger magnetic fields to be picked up by the pickup coil. So it produces lots of eddy currents, a much stronger eddy currents and stronger return magnetic fields. But then we can have a much smaller, right? Those aren't going to be anywhere near as strong as the magnetic field created by the driver coil, especially in materials like aluminum and titanium that are not ferromagnetic. They don't really want to create a magnetic field very well. So then we have a pickup coil that's much smaller and more sensitive to those relatively small, relatively weak fields that are generated by the eddy currents. And that way the driver, the power being sent in to drive the coil will not overwhelm the ultimate signal coming back through the pickup coil. When you're using any of these probes, if you overwhelm it, you'll get an indication on your display. I'll show it in lab when we do the demo. You'll see I'm trying to remember the exact wording on it, but it's essentially an oversaturation box comes up. It tells you you're getting a lot of distortion and feedback in your coil. And if you're getting that, your results are not acceptable. That's basically a false indication. So these coils, the reflection coils, help to minimize that from occurring. So indications from these can look both ways as well. Oftentimes they're very similar to our absolute coil because, again, we're really only looking at that coil. Only one coil is going to be affected that we're actually looking at, right? We're not comparing the two coils now. We're just looking at the pickup coil. And so often the indications will look a lot like an absolute, but in some cases, again, depending on how the coils are arranged, one above the other, one next to the other, or how wide it is, one inside of the other. Sometimes they do the driver coil wound around the outside of the pickup coil in the center. You might get the bow tie, or you may get similar to the absolute probe, but where it actually creates little loops and lines. So you can see at the end of the day, what the screen does, what you see on the screen, doesn't really ultimately matter. You just need to know what you're looking for. And that's why we use a reference standard. So before you go test your airplane, before you go test your wheel, right, before you do your fuselage skin to check for cracks around rivets, before you look for cracks in the bead seat of the wheel, you have to use a reference standard that has a known good area and a known bad area, right? And by comparing those known good to known bad, you can get an idea of what kind of an indication you should be looking for when you go to your unknown part, to your aircraft fuselage, to your wheel bead, to your trunnion pin, to your, there's all kinds of those different objects on the aircraft that you may use these for. So the actual indication, like what you're getting, just know it can look different. You can see typically we're putting the origin somewhere around the lower right corner, except if you know you're going to get one of these bow tie ones, you probably don't want to put it right down here, right? If you know you're going to get a bow tie style indication, you probably want to put it more in the middle of the screen. But otherwise, most of the time we want to orient it so that our origin's down here. What you're also seeing on here, kind of another thing, remember I said there's an indication where the probe was set on the part or it was removed? That's called liftoff. That's this line across the bottom that's going off the side of the screen. And that's a major, right? You're going to get the biggest change in inductive reactance is when you put the coil on the part or take it away, right? That's the biggest change in the amount of metal in front of the coil. So that's that. That is your liftoff, which we typically want to make horizontal if possible. So here, what they've done is gotten a liftoff, set the probe on the part, and then cleared the screen before doing the inspection. Now you can clear the screen at any point, but remember, this is a graph essentially over time of the inductive reactance of the coil. And then the hybrid probe, I mentioned earlier is a mix of these two. So describes a coil arrangement that's not standard or that doesn't necessarily fit into one of those other categories. It may have some attributes of absolute. It may have some attributes of differential. It may have some attributes of a reflection probe. It may have, more than one in those cases. So typically some kind of a combination, and often for special applications. Other things they can do, additional coils for multi-frequency testing. So you may have some large probes and some small probes. The large probes would run at a lower frequency, lower coils, coils. Large coils, small coils. The larger coils are driven at a lower frequency, gives you greater depth of penetration. Less sensitive, but you're going to see further into the part. The small coils are driven at a higher frequency. They get less penetration into the part, but they're more sensitive to small flaws near the surface. And so a probe can be doing both. It can be inspecting both the front and backside surfaces for cracks and corrosion. So here are just some examples of wiring diagrams of some of these different probes. So here is our absolute probe, and this is an absolute probe where they show a reference coil. Okay, so that's that air-loaded coil so that it can compare that, and they show, resistors. This is OSC is your frequency generator, and then the detector. So the detector portion, this OSC, which is the frequency generator, some of these resistors, that's up in the test unit, typically. It can be in the probe sometimes if it needs some extra. But then they have a bridge type probe here. That is a form of differential probe, excuse me. Because here you have two driven coils in the bridge type probe. It's a reflection or a differential probe. You got two coils, and the detector is looking at both of them and comparing them. Okay. The ones on the right are reflection probes. So here you can see the driver in the upper one here. There's a driver and a pickup coil, so you can see the detectors primarily looking at the pickup in this case. Or below that, it shows a reflection style where you have multiple coils on the driven side, multiple coils on the pickup side. But again, the two coils on the left here are driven, are getting current run into them. The two coils on the right are hooked to the detector. They're not tied to each other, so that's where it's still a reflection probe, even though it's got 4 coils built into it. And then the two on the bottom there are forms of hybrid probes. So this first one they call a bridge differential. You can see it's not much different than the bridge probe up there. Looks pretty close. The difference is kind of how the differential display. It's whether you're getting more, remember I said a differential probe, you can get kind of an absolute looking display or a differential type display. So it has to deal with the reactivity of the probe and how it's interacting with the surface. This reflection differential is definitely a hybrid probe. You can see it's got a detector wired to two pickups that are in a differential or in a reflection type arrangement. Okay. But because there's two there, it's also kind of a differential type arrangement as well. It can look at the difference between these two coils, but they're not being driven by the frequency generator directly. Same picture, just made them a little bigger. We can also take any of these, absolute, bridge, differential, reflection, and we can put multiple into a single sensor. So what we have here is something called an array. We have a couple array probes. So what they mean by array is basically multiple probes in one piece. So this is a flexible array. It can be made to fit different surfaces. Or you can have all these kind of dots on here are various coils to run along a contoured surface. And so when you start doing that, you can do some pretty neat stuff. So I'm going to stop here. I'll play the video as kind of the last bit of class today. And then we'll get into shielding, loading, and processes next time.